So here's where we left off. We were talking about numbers. Let's just back up a tiny bit. Remember we did this. We looked at this. I want you to go ahead and click all your Chromebooks closed, please. Put your phones away, all that good stuff. So we were talking about quadrilaterals. We said the set of all quadrilaterals is a very big set. And then inside that big set are some smaller subsets. So the set of parallelograms is a set inside the set of quadrilaterals. So we call that a subset. Inside the set of parallelograms is an even smaller subset of rectangles. And inside the set of rectangles is an even smaller subset of squares. So there's a lot more quadrilaterals than there are just squares, right? This has gotten more specific. We started very general and we got more specific. Okay, we're going to take a different look at this today. So we looked at this one way, which was with a, kind of a tree chart here. If you've got earbuds or anything too, please take those out, put those away. Let's look at it with a slightly different approach. Let's look at this with what's called a Venn diagram. So this is a Venn diagram. You guys have seen stuff like this, right? Okay. What does this mean? So we've got the set of all quadrilaterals. Make that red. So inside this big red bubble then, imagine this is where we're putting all of the possible quadrilaterals that we could make. They all are getting dumped into this big red set. Okay, inside the set of quadrilaterals is a smaller subset. In this case, we're looking at the subset of parallelograms. Notice that the purple set is completely contained inside the red set because the purple set is a subset of the red set. All parallelograms are quadrilaterals, but there are some quadrilaterals that are outside of the purple set that aren't parallelograms, right? Okay, and then we could even go further. Inside the set of parallelograms, we could say there's a set of rectangles. So the green bubble or the green set contains all the rectangles and so on and so forth. We could just keep going if we wanted to. And then we started applying that to numbers. And we said, okay, we said right away we could take the whole set of numbers and we could break that down into the set of real numbers, which is every number you've ever seen, and then these weird imaginary numbers you've never seen, but we will see soon, okay? And the real numbers, we could keep going. We could break those down even a little bit further, right? So the set of real numbers, we could break down into rational numbers and irrational numbers, okay? So every real number has to be either a rational number or an irrational number. There's no other option, one or the other. If it's a rational number, we said that can be written as a fraction. Irrational numbers cannot be written as a fraction then. If we were to write these as decimals, rational numbers always either repeat or terminate, right? And we use a bar to indicate the part of the packet that's repeating. Like if I were, let's do one other example of this. Like if I were going to do something like, for example, what if I did something like 1/7? One-seventh is 0.14. Oh, what is this? Somebody look at this on your calculator for me. 1/4. No, it's something like would be like 1/4. 285 or something like that. 285. Yeah, that's what I thought. 285, and then it's 14285 or 07 there. 142857. Right. So all it did is it rounded that 857 up to a 9. But if your calculator's display was bigger, you would see that it's just repeating this packet of 142857 over and over again. So 0.142857, 142857, 142857, on and on and on, right? So how do we indicate then the part that's repeating? Okay, good. So the bar in this case would go over all that stuff because all that stuff is being repeated, okay? And as strange as these look, when I write a decimal like that, it means that it really goes forever, and that forever decimal, that infinite decimal, is exactly equal to the fraction. So we can put an equal sign there, just like we could with the terminating decimal. 3/4 is exactly equal to 0.75. Okay, what about pi though? Okay, pi is a different example. Pi is an irrational number. If we write that as a decimal, it's 3.14159, blah, blah, blah. It goes on and on and on forever and ever, right? Now, that's what the dot, dot, dot means. It never repeats and never terminates, but just goes on and on and on forever and ever, okay? So irrational numbers, again, they never repeat or terminate. And we know that logically because all real numbers are either rational or irrational, and every rational number either repeats or terminates. So the irrational numbers couldn't do either one of those things, right? Okay. And notice that we don't use an equal sign here. What does this mean again? I think you told me yesterday. When we do a squiggly equals like that, approximately. So pi is approximately equal to 3.14159, for example. Okay. Anytime we write an irrational number as a decimal, technically we'd always have to write it with an approximately equal because it's never going to be exactly equal. We always have to round it at some point. What's the best way to write pi? The symbol. Yeah, because the symbol means exactly pi. Good. Okay? All right, so inside the set of rational numbers, we've broken down real numbers into rational numbers and irrational numbers. We're not going to go any further with the irrational numbers. That's as far as we're going to break that set down. But rational numbers, we could look further and look at some other subsets. This is written kind of backwards. This is a little inconvenient. But we're kind of starting at integers and we're working our way up. So we're working from general to specific in this order, right? We said that rational numbers are fractions, the set of all numbers that can be written as fractions. Well, integers are just a special subset of that. Would you guys all agree that if I were to put a 1 underneath the 2, what's 2 over 1 equal to? 2, right? I mean, we don't really write the denominator of 1, but it's there. Technically, it is a fraction. Same thing with -3. It's really -3 over 1. We just don't bother writing the divided by -1. So all of the fractions that have 1 for a denominator are what we call the integers, right? Another way of thinking about that is if you think back to grade school when you were working with number lines, those were just the dashes on the number line, right? That went forever and ever. The dashes were always at the integers, okay? Well, inside that set of integers, what if we just took away the negative numbers? Then you're left with the set that starts at 0 and just counts up by 1. We call that the set of whole numbers. Now, would you guys all agree that integers are a subset of rational numbers? It's just a special set of fractions. And then the whole numbers, that's a set that's contained inside the set of integers. So whole numbers are a subset of integers. And then if we just took the 1 away, we're left with the smallest set, which is the set of natural numbers. Okay? And we could represent these things like that. It's one way to do it. Real numbers split into either rational numbers or irrational numbers. Irrational numbers we'll just stop with, but if we look at the rational numbers, those would break down into the integers, or the other possibility would be the fractions that have other denominators than 1, right? If we focus on the integers, we could break those up into whole numbers or negative numbers, right? That's not a set that we're going to focus on, but if it's not a whole number, the integer must be a negative number. The whole numbers we could break down into 0 or the even smaller set of natural numbers. And probably the best way to look at this is like that. There's that Venn diagram. That really tells the story more easily, I think. You've got this big blue set of real numbers. Inside the real numbers, you've got this subset of irrational numbers that's all by itself. And you've got this other subset of rational numbers that's by itself. But inside the set of rational numbers, you've got another subset of just the integers. Inside the integers, you have a subset of just the whole numbers. And inside the whole numbers, you have the smallest subset, which is the subset of the natural numbers. Okay, give me a thumbs up for real good, thumbs down for don't get it, thumbs sideways for I'm getting there, kind of a thing. Thumbs up, thumb down. So, okay, we're looking, all right, not bad. We'll continue on. It'll get clearer. The more further we go, the clearer it gets. Okay, so these are all rational numbers. So what if we wanted to write these as decimals? Really all this slide is about is just how do we write these as decimals? Well, what's the easiest way to turn something like -5/7 into a decimal? Calculator, right? Just type it in a calculator. But the key is you have to make sure if it's a fraction, you got to go until you see a repeating pattern so you can put that bar on it. So somebody with your phone is fine. Just turn your phone sideways and tell me what's -5.7. What's that work out to be as a decimal? Seven one something. Two eight seven. What is it? Somebody got it for me? Anton's getting it. 285, something like that. 42857142. Then it starts to repeat again. Okay, so that's what we have to go out quite a ways for that one, but we see it does repeat. Okay, 15/5. That's easy. What's that? 3. That's an integer, right? And then 13/25. Don't use your calculator. We can do this one without. What goes there? Yeah, 52. Good. I could multiply both the top and the bottom by 4, couldn't I? Okay. Which tells us that this is just 0.52, right? Okay. And you could use a calculator if you wanted to. Okay, what about these? So here's the game we're playing here. We're going to determine whether each of these is rational or irrational. So you're going to give me thumbs up for rational, thumbs down for irrational. First one, rational or irrational? Oh, I'm seeing thumbs up, even though it's a square root. How come? It's just 5. Yeah. So the moral of the story here is you always want to simplify whatever you're looking at first. Write it as simply as possible. The square root of 25 is just 5. So that's rational. Well, obviously B and D, what are those? Rational or irrational? Rational. They're fractions, right? So they can be written as a fraction. So those are clearly rational. What about C? Yeah, that's thumbs down because it's a square root and it doesn't simplify to an integer. So anytime I have a square root that doesn't turn into just an integer answer, a whole number answer actually, we know we're done, right? It's got to be irrational. Now the bottom one is tricky. What do you think? That's right. Yeah. Okay, I'm seeing a little bit of both. Why is it irrational? How come it sure looks like it's trying to be rational? How come it's irrational? Okay, it doesn't repeat. You can see there's kind of a pattern there, but it's not a repeating pattern. Good. So that's irrational. Okay, and there's the explanation, right? Yeah, there is some kind of, it looks like there's a building pattern, but the number of 3s changes each time, and so it never repeats. Okay, we can skip that. We already talked about that. I think, do I want me to do anything? No, we're good with that. Okay, so here is, oh man, this guy, okay. I'm just going to skip this one. Okay, I actually like, I actually like this Venn diagram better. See if you can tell me why. I like this one a little bit better than that one. Why is that? Let's get phones away, please. So, how come? This is the one we started with. It's fine. It's not like it's terrible. It's okay. I like this one a little bit better. Anybody tell me why? I'll be really impressed if somebody can tell me why. There's a really subtle difference. Let me give you a hint. What do you think? Yes, sir. No, that's a good. I mean, it's perceptive. You saw that. That's so they give more kinds of numbers. That's not really what does it for me. Ooh, almost. I'm gonna give you a hint. Remember, I told you that all real numbers have to be either rational or irrational. There's no other alternative. But what about this one just seems a little bit, it's not quite as good. Okay, it doesn't divide them as prominently. Look what happens here. Here we've got this set of the blue set of real numbers, and then inside that we've got the subset of rational numbers and the set of irrational numbers. But notice it kind of leaves this extra space in there. It almost implies that, for example, like right there, that there's room for another real number that's neither rational nor irrational. Is that possible? Can't do that, can you? If you're a real number, you have to either be rational or irrational. So if we use this Venn diagram, I mean, it's okay, but we have to remember that we could never put any numbers in this part of the real number set. So for that reason, I actually kind of like this one just a little bit better because now there's no man's land there, right? The big rectangle of real numbers is divided into only two pieces. The lime green, I guess you'd call that, right? The green part that contains rational numbers and the red part that contains the irrational numbers. There is no other place. So I sort of like that one a little bit better. And then I just want to demonstrate here that we could go a lot further with this. We could make a much more complicated, sophisticated looking Venn diagram where there's lots of other stuff going on too. We're not going to deal with that really, but we could. In a future math class, we might want to look at things like transcendental numbers or algebraic numbers. This year, we will look at imaginary numbers and complex numbers. So that actually is coming down the pike here in the future. Okay, so why don't you guys got the handouts, right, from yesterday? Grab that handout and let's just fill in some notes here. You need one? Okay. That's all right. I've got one for you. There you go. Okay, so just a quick summary, right? The real numbers consist of the following sets. We have the irrationals and the rationals are broken up into these subsets, okay? The symbol we use for the set of real numbers is capital R, okay? That we're going to use on our notes. Different textbooks use different symbols, but we're going to stick with R. For R is real numbers is always R. Okay, the set of irrational numbers, a lot of times, rational numbers usually is Q. For whatever reason, Q is usually, I guess because R has already been used. So rational numbers are Q. A lot of times, and I actually like this better, the set of irrational numbers we'd call Q prime, okay, but not in our notes. In our notes, we're using I for irrationals, okay? But different textbooks will treat that differently. So the set of integers then, I's already been used, so the set of integers is Z, and that's pretty common. Pretty common. Usually we use Z for integers. Whole numbers, we don't even really use that much, but that's W, and natural numbers is N. Okay, so where would we put these then? Let's try to place all those symbols in this Venn diagram. So what should the big rectangle probably be? Good, that's the set of all reals. Now this isn't such a good one because we've got a no man's land here, but what do you think that little isolated subset must be? That's got to be irrational, doesn't it? So that's going to be I. What would the bigger subset be? Real. Okay. What's the next biggest subset that real numbers contains? Integers. Okay, but there are some. Oops, that's not supposed to be an R. Whoops, my mistake. Don't do that. Don't make that an R. What's that supposed to be? Q. There you go. Q for rational. There are some rational numbers that aren't integers though, and those would go up there, wouldn't they? Right? What's that? Oh gosh, what did I put? That's not what that's supposed to be. That's supposed to be a Z. I'm really messing up, aren't I? Yeah. Whoops. Integers are supposed to be a Z. Then what's inside integers? Whole numbers. There. Now we're back on track. Whole numbers, and then natural numbers. So let's throw a couple samples in there. So irrational numbers, that would be something like pi, or maybe the square root of 2. Rational numbers would be things like maybe 2/7 or 0.3 repeating, or 0. Oops, I guess we can hang on a second here. Yeah, 0.3 repeating, or 0.5, right? Also, rational numbers that are integers would be things like -3 and 0 and 4, right? But 4 would be a natural number. 0 would also be a whole number. -3 would only be an integer. Does that make sense? Okay. And then rather than me writing all those examples in, there's just some examples for you. What a great place to end. You can't teach that timing. Oh my goodness. Have a great day.